Everyone assembles here. Just a reminder, tonight we have a really interesting social happening at the USS, on the USS Midway. Yeah, USS Midway. So just a reminder to come out there and see this massive ship and all the interesting things they have to show us. I heard there's some great flight simulators and whatnot, so it should be pretty cool.
Wow, that's a massive clock. So welcome to NANOG 54. It's kind of nice to be up here and not be the program committee chair. It's like nice to have somebody else have that job. But it's still nice to see all of the folks out here. So it's great to see you all here. So this panel is on OpenFlow and the related technologies. We got quite a few inquiries and decided we'd try to do a panel on this. We had a couple of talks last time. And this particular panel is supposed to kind of be driving at, the difference between fact and fiction and what's real and what's not real. So we have three people who are active in the industry. We have, let's see, we have Guido, see if I can get the last name right. How do you pronounce your last name? Appenzeller. Okay, so there you go. He's CTO of Big Switch, which is one of the startups in the space. Ed Crabb, Google, and Kirk Beckman from Brocade. And all of these folks will give us a different, or sort of their view of what the state of the art is, where this is going, and what the difference between fact and fiction is. So now all we have to do is figure out. So I guess we're going to do it Guido, Kurt, and then Ed. So how do we cue the slide decks? Can you do that? And then I guess this is the device. Wow, this is fancy. So would you like to get up here?
All right, super. Can you hear me? Thanks. So when I put together my slides trying to answer the question, what's real and what's virtual about OpenFlow, the first thing I did was go back and ask, when did we start this whole thing? And I'm not sure if everybody can read this, but if you look at the OpenFlow website, the first draft of the OpenFlow spec was actually published in November 2007. And if you read further, it says there's a little footnote that the final spec is expected for early 2008. The actual OpenFlow 1.0 spec was actually published in December 31st, 2009, so almost early 2010, so 2 years late. And so I asked myself, well, how did it happen that it took so much longer than we initially expected, the original designers expected? And I think for me personally, the answer is, I think building a centralized control plane, which is essentially what OpenFlow is about, turns out to be a lot harder than we originally thought. I'm proud to say that during my time at Stanford, we figured out ways to melt down the network that at least I had not previously thought about. But I think the good news is that at the end of this process of figuring out how to build centralized control planes is that today we have a rough architecture for OpenFlow that is emerging and that seems to be working pretty well. And the architecture is shown here. So to build an OpenFlow-based system, we basically have three major pieces. We have the data plane. So these are switches. It can be software switches or hardware switches. For this talk, I'll mostly talk about hardware switches that basically are enabled with the OpenFlow protocol. We have a controller platform that basically talks to the switches and exposes an API up on top to the applications running on top of it. And then we have applications that actually provide the new interesting services in the network that we want. So for this talk, I'm going to keep it fairly simple. I just want to talk about sort of our perspective and what we're seeing for the data plane, for the switches, for the controller platforms, and for the applications. So again, a little bit of history. Here's sort of a rough timeline of the OpenFlow specification, from 2007 to today. OpenFlow 1.2 actually has been approved by the Open Networking Foundation, but it's currently in embargo period where it's not public yet. But that should change in the next month or so. If you, in parallel to the standards development, look at how switches have been developed. In mid-2008, we started to do first research demos. I think the first ones were NEC, Cisco, Juniper, and HP. In 2010, we started seeing the development of these implementations move out of research lab, out of universities, more into the development units of the switch vendors. And then it was only in actually it was mid last year, in May, that NEC, as the first company, offered a generally available OpenFlow switch, followed by IBM late last year, and then HP early this year. So we only have been building generally available OpenFlow switches for about 6 months now. The really interesting question is what's going to happen next, and I think the best is still to come. I think for the rest of this year, we'll see a number of additional vendors come with their switches, and I'm very, very excited about what I've seen in the product pipelines of some of the manufacturers there. To give you a brief overview of what can OpenFlow switches do today, so the most common OpenFlow switch we have is sort of a pizza box top of rack type design. It comes in 10 gig or 1 gig flavors, so high density 10 gig, 48 ports or 64 ports, many ports of 1 gig. There's also a modular, a small chassis switch available from HP, the 5406. In terms of capabilities, these switches typically implement most of OpenFlow 1.0 with a couple of caveats. So this means they can match on layer 2, layer 3 headers and TCP port. We have basic rewriting capabilities. They typically all support L2. L3 support is limited. Specifically, we don't have a mechanism for TTL decrement yet, which limits how useful they are for routing. And the flow table size, meaning the number of OpenFlow rules you can actually put in one of these switches, is typically less than 10K entries. The one exception being the NEC switch that has an external TCAM, so it can go up to about 160,000 entries. And all of these switches are hybrid, meaning there's an existing switching stack, a normal software from the vendor. In addition to that, there's an OpenFlow stack on it. There's one exception, which is the white branded switches sold on the Pronto label. Basically, where you can put Open vSwitch or Indigo, so open source implementations on it. And at that point, you get a pure OpenFlow switch that really has no other way to control the switch. And all of them have, these are switching chips, so they have very small buffers. So as of today, there's 4 different vendors that'll basically sell you an OpenFlow switch, if you ask them. I've personally seen about 15 different hardware vendors demo OpenFlow switches at different points in time. My prediction is the number of commercially available OpenFlow-enabled hardware will definitely double this year, but probably grow even faster. So this should be a very exciting year for the OpenFlow community. The next thing you need to build an OpenFlow system is an OpenFlow controller. If you look at a controller, it basically has two fundamental APIs you care about. The southbound API, it talks to the switches or the network elements, and that talks to the OpenFlow protocol. More generally, these controllers are often SDN controllers, so they might talk other protocols to these switches as well. And then there's a northbound API. Basically, what the controller tries to do there is to provide an interface to applications sitting on top of it that represent the entire network and not each network element individually. So for example, I can query this API to say, please give me the entire topology of the network, or find a shortest path from A to B, or set up a flow from a source to a destination. So basically I can reason about the network as a whole. A lot of the complexity of the controller platform is basically figuring out how to build a distributed system, with eventual consistency guarantees that then exposes a certain set of these unified, centralized APIs to the top. Today, if you want to try out OpenFlow, there's a number of open source controllers that are pretty interesting. I have a list here, and you can read faster than I can talk. They differ in terms of languages they're written in terms of licenses. As a shameless plug here, we are actually commercially supporting Floodlight, which is one of the OpenFlow controllers written in Java, and it's fairly high performant, used by a number of companies for their products. If you're looking for commercial controllers, the big differentiator between what's currently available as open source and as commercial controllers is typically that the commercial ones have a couple of features which you'll probably want for large deployments, such as high availability, meaning you can run with multiple nodes, scale out. In some cases, you can actually have partition-tolerant controllers that you can basically run across multiple data centers. They'll continue to function, if the links between the different failure domains go down. To the extent that I can tell, we currently have a couple of mid-sized deployments running for about a year or so with production traffic that's growing. We'll see more of these appear this year. And so if there are differences in controllers, some of the controllers only work with switches from the same vendor, while other controllers, they will work with a variety of different switch models from different vendors. So last but not least, let me talk about what are the use cases, what are actually the applications that are sitting on top of this. I think If there's something like a killer app for OpenFlow, from my perspective, it's probably network virtualization. I'd be curious to hear what the other speakers are thinking. But you know, the basic use case there is that you have a virtualized data center. You know, you basically have racks of servers, either virtualized or not, where basically you have multiple tenants, and you want to take a subset of hosts, either physical hosts or virtual machines, put them on a separate network, you know, isolate that network, you know, create a separate broadcast domain, potentially deploy a particular service model on top of that, and then basically create this virtual network or virtual switch that you've created, delegate that out to one of your tenants. You know, there's several companies working this use case, and it seems to be a pretty broad interest, you know, from customers in this across both enterprise and service provider. The other thing you can do with an OpenFlow controller is you can write your own applications. So here's a little bit of pseudocode, you know, to show what you can do here. In general, programming your network directly with OpenFlow tends to be hard because you still have to talk to every separate network device, you know, individually. You have to basically worry about what if they go down, what if they reset state, you know, make sure that, you know, what about, you know, making sure you converge in terms of the intermediate state that you're gathering. With SDN, with the control platform, it becomes a lot easier because now you have a centralized API which can query about the state of the entire network. So here's a little bit of pseudocode, for example, if you want to essentially set up, you know, take a flow between two end hosts and, you know, map it to a different priority queue in your network to give it some QoS guarantees. You know, in general, that's a hard problem because you first have to find those hosts. You know, if you have lots of switches, you may or may not have infrastructure in place to find it automatically. Then you have to determine paths and so on. With OpenFlow, you can potentially do this much, much easier by basically directly querying the controller platform and saying, where are these hosts? And, you know, give me a shortest path between them. And now I'm basically just insert flow table entries that'll forward this flow along this path. And, you know, then you can subscribe to an event, basically saying, you know, I want to get all notifications if hosts move. So if I see a host move on the network, in that case, allow me to, so I can recompute, you know, what's happening in my network. This is a gross oversimplification, but I think you get the idea of what's possible with this platform. So last but not least, in order to get a little bit of discussion going here, I thought I'd make some predictions for what we're going to see this year. You know, I think in 2012, my guess is most switch and router hardware vendors will announce an OpenFlow or at least SDN strategy of some type. You know, of those vendors, I think the majority will actually have devices available, generally available in the market. And you know, I think we'll also see a fair number of mid to large scale deployments that become public, primarily led initially by data center deployments, but then going beyond that. Thanks.
What I was thinking we'd do would kind of like aggregate all the questions for the end. So unless somebody has questions right now, we'll just go on to the next speaker and we'll get them at the end. So, Kurt.
Thanks, Dave. This is my first NANOG, and I'm glad to be here. And I was lucky enough to run into Bill Norton at the airport, and he shared his internet peering book with me by way of welcoming me. And he's got a little anecdote about what happened actually at this end of the flight in the book. So stop by and talk to him about that. It's a little bit entertaining. Yeah, we're going to need the. You want to go next to Ed? No.
They're switching over now.
Yeah.
Can you guys swap the decks?
I do pretty much agree with Guido's predictions. Not overly bold, but appropriate for the market. But we'll see. Maybe I'll be wrong too. All right. So here are my slides. My name is Kurt Beckman. I'm with Brocade. Draft slides. Well, I changed this. I wonder if these are the slides I thought they were, but let's find out. So first I want to touch on the conventional wisdom about OpenFlow. We get a lot of contradictory statements out here. So Scott Schenker, one of the fathers of OpenFlow, there are several fathers, said more than once, OpenFlow doesn't let you do anything new or anything that you couldn't do before. And you think, really? Well, if that's true, you know, why would I care? Why do I care about OpenFlow if I can't do anything new? But his next sentence was to say, but it does give you a programmatic interface. So if you're an independent software developer, now you can do something that you couldn't do before, and that's kind of interesting. Or if you're a network operator that has the capability of coding, you've got developers, now you can do some new things. Sure, if you're a switch developer, like Brocade, OpenFlow doesn't let you do much new, but the interesting bit's in that programmatic interface. It enables all kinds of possibilities. And in a number of these other meetings, you'll see people talk more about the possibilities. Guido mentioned the virtualized networking inside the data center. You can virtualize networks outside the data center as well. There's a number of applications, traffic engineering and so on, and hopefully Ed will talk more about that. I'm not going into a lot of the applications. So that's what you can do, sort of. As Guido mentioned, most people are have adopted 1.0. 1.1's not getting a lot of adoption. 1.2 that'll come out in a few days, really, come out of embargo. There's not been a lot of commitments about it. People talk about it, but will it be adopted? It's hard to say. And there's reasons for that I might talk about in a little bit. So OpenFlow today, the standard as it exists, there's lots of gaps. It's really early days, and so it's not today's versions of the standard that enable this, but it's the idea of OpenFlow that enables these things. So historically, we hardware vendors have controlled the software, and we've paid for the software development through selling hardware. And that has constrained the pace of innovation. So when soft switches became part of the game a few years ago with hypervisors and so on, that altered the game a little bit, and now OpenFlow alters it in a bigger way as vendors adopt it. So we can expect to see much more rapid innovation going forward, because we'll now be iterating at a software kind of a pace instead of the hardware, every 6 to 9 months you get a new release. So good news, bad news. Software-defined networking, of which OpenFlow is a prominent part, it gives you the power to do whatever you want, and of course that naturally means that you don't have enough rope to hang yourself if you're not careful. So be careful. And the number of interesting applications is huge. Well, that's good news. There's a big market. But on the other hand, in the standards body, it means there's a million voices, and it's hard for us to prioritize and figure out how to implement, because the right thing for somebody is the wrong thing for somebody else, and so things go a little bit slow. People like to use the compute stack. Oh, we've got this really sweet compute stack. It's nicely layered. We've got vendors competing in every aspect of that compute stack. Wouldn't it be nice if we do that in networking? It's a familiar framework and helpful, but we're not in the same position. We don't have the equivalent of an Intel yet, and actually lots of other differences. It's much more widely deployed than computing was when the compute stack was developing. So we have this legacy of existing hardware that OpenFlow wants to work on, and that kind of complicates life a lot. So we need to figure out how we're going to move to that networking stack, given where we are in the life cycle of networking. So one thing I like to do is talk about expectations. It really bugs me when we can't deliver on expectations, because the expectations are just so far out ahead of reality. So I'm doing a couple slides on that here. So there's some contradictions that you often see in here, because people are working in different time scales. There's the time scale of, can I buy something, and I need to plan for that, and then there's the time scale about, oh, there's the future, and I want you to be excited about this OpenFlow thing and support it and express interest so that vendors pursue it. OpenFlow 1.0 and 1.1 are pretty limited. 1.2 is added some stuff, but it also has gaps. IPv6 was missing from those first two versions. There's a little bit more in 1.2. High availability is not part of the spec. People have implemented it, but it's outside the spec or beyond the spec. Configuration is now coming up to speed, but it wasn't in those early ones, and topology discover, and you can go on. There's just lots of stuff missing. There's a lot of cool demos. I'll show you a link later on. People are demonstrating this, but there is really either a constrained environment, or maybe they did some extensions, or they're operating a little bit beyond the spec, et cetera. So a lot of this cool stuff it's definitely going to come. I mean, I'm a believer in OpenFlow, and is it within your planning horizon? Well, it depends on your planning horizon and sort of what problem you're looking to solve and when. ONF is, 1.2, as we said, is coming right out, and 1.3 and 1.4 will be out later this year. So they're taking a little bit different approach to standards development. It doesn't come out when it's ready necessarily. We're trying to push to deadlines, and that's getting us to be more productive, but some things often miss the deadlines. So it's coming out kind of chunky. So we've had some V6, but missed some other V6, for example. And there's going to continue to be more useful stuff added. Guido sort of mentioned, well, both of us, the hardware developers are mostly running on 1.0 version of the spec. There's some aspects of 1.1, well, I think it says that. I'll talk about that in a little bit, sorry. 10,000 foot view, let's step back from the ones and zeros. Right now, we don't have certification. There is a testing working group. We're going to have a plug fest in a few weeks, and that'll get us somewhere, but it's still not the same as conformance testing. That's also being worked, but it's a little ways off. So prior to that stage, interoperability isn't guaranteed at all. So the way you provide a solution is you partner with folks. And so as customers, either prepare to, if you're going to write your own controller, prepare to partner with a switch vendor. If you're going to buy a controller, you're going to have to sort of work with two companies to do that. You don't just go get a, mix and match. I'll get one of these and I'll hook it up to whatever I feel like it. So, and you also may not find the app that you're looking for. If you're going to write your own application, you don't care, but then you still want to know, okay, well, which are the switches that can do what I need it to do? And also, there's been a lot of talk about how OpenFlow is just going to commoditize the switch and really drive down pricing. But in the near term, switch vendors are taking existing switches and adding some OpenFlow interface to it. So that means it's incrementally more work, not less work. It's not going to drive down the cost in the near term, especially when you don't have strong interoperability and competitiveness in that way. In the medium term, we'll get a lot more interoperability. Basic applications, whatever those are, should be able to work on more than one box. But the more interesting applications will probably require additional extensions or answering questions that kind of go beyond what the spec can answer. And so even with certifications, they'll still be partnering in order to deliver really interesting applications. And also, you will see vendors focusing on specific application spaces. They can't take on the whole market, or the whole potential market. It's just too big and there's too much going on. And then in the longer term, interoperability will be much less of a problem. I expect you'll see some consolidations, and there'll be, big and trusted vendors in the space. And you probably, if you're not in a real tiny niche, you'll probably be able to find the applications that you want and get some interoperability. So a lot of people ask, how can you engage in OpenFlow? I mean, what are the different ways you can participate? And well, it sort of depends who you are, of course, and I decided I'd slice that space in terms of how many resources you have and what kind of challenges you face. And that's not a very, not this whole space is interesting. There's only some of these spaces that really make sense. If you're underwater in terms of resources and at the cutting edge, you should just bail. You're not going to be able to accomplish much. So that's not a realistic space. And in the other corner, you have tons of time and you're not very much demanding environment. I don't think very many people in this room are in either of those corners. It's going to be more along the diagonal. If you haven't got any resources and you've basically overloaded, you got some challenges, but you're overloaded, then skim the blogs during your minimal lunchtime. Otherwise, watch the demos, and this is the URL. You can go to openflow.org. There are good demos there that give you a sense about what the applications are, the potential applications that people have been thinking about, and they're quite interesting and diverse. And you can read the specs that are posted online. They're quite readable. Guido posted the 1.0 version. 1.2 will be, I think, posted, as I said, in the next few days. It exists, and nobody's been talking about fires burning with issues during the embargo, so that should be up shortly. After that, you can do an OpenFlow tutorial. It's online. There's a link there. And all the materials there, and it runs in a hypervisor on your laptop if you want. So in terms of resources, it's pretty easy to go through that. I've done it, and it's nice to do it at one of the meetings where there's a bunch of experts wandering around, but you can do it on your own and pretty well make sense of it and get a feel for what this OpenFlow is currently able to do today, and not necessarily where it's going. And then you can take and expand that if you've got more resources and it's more interesting to you, because if you're out in the bleeding edges where OpenFlow gets interesting, because that's where the problems are not solved as well as you would like them to be. Then if you're more time and more challenges in your environment, you should get that stuff in your lab, get some units and put it through its paces. And as Guido said, there's vendors that, several vendors that offer stuff for sale today, and I think some other vendors, one I know of in particular, that you can get stuff in your lab even though it's not technically for sale yet. Then you can become active in ONF. Of course, that I've got you over on the right side of the resources there. That means you can write the check. It's not a huge check. Some customers are able to write that check. Beyond that, then deploy it in a pre-production or a pre-standard thing in production. And then if you're really bold, you can write your own application. And I think that was the last, no, okay, good. I will add slides. So these were the draft slides. I submitted more slides last night, but we ended up with the ones that I submitted 3 weeks ago. I do want to say a couple things about 1.1 and 1.2. So they added 1.1 and 1.2. No, I'll take another step back to 1.0. 1.0 was a very simplistic model. A single sort of TCAM-like table was the assumption of what existed in the switch. And people could get clever about how they programmed that table and maybe loop back around that table, which is slightly out of the standard, but you could do clever searching or matching and actions based on that. And most switches were able to support that, but it was complicated to achieve things because of that limited architecture. So 1.1, it added a couple of key things. It added support for groups, and it also allowed for multiple tables with a mechanism to have a go-to action from one table to get to another table and do further matching and further actions and further go-tos and so on. Well, that was very powerful. You can do all kinds of things with that model. Unfortunately, it's much harder from a hardware vendor with an existing ASIC that was not designed for OpenFlow to figure out, okay, so how do I take these requests, these table entries, how do I map that to my resources in my ASIC? I mean, I have many tables, but very often I do my lookups in parallel, and this thing's got its go-to, and I'm not even going to try. It's just too hard to figure out how to do that. And that same model exists for 1.2 and looks like it'll exist for 1.3. So software implementations or NPU, network processor unit implementations, are able to essentially emulate that. They're very flexible. It's not a problem. So you see one part of the OpenFlow world is comfortable with these 1.1 and 1.2 implementations. And then hardware vendors like Brocade look at that and kind of struggle, and so we just continue to use 1.0 and add an extension here or an addition there. Meanwhile, in ONF, there's a recognition that not both sides, not both kinds of switches, software and hardware, soft and hard, are sort of equally supported. And so there's a lot of flurry of activity with bursts of progress toward addressing that issue. And I'm happy that we're making good progress. I wish we were making it faster, but there will be some changes probably later this year that will really allow the hardware-based switches to join the party in a better way with full standards compliance versus the kind of divergent stuff that they're doing now. So thank you, and I'll pass the baton back to Dave.
So again, I think we'll, unless anybody has any questions right now, we'll go to Ed, and then we'll do questions.
All right. Morning all, or not morning anymore. So I am not trying to sell you anything. I work at Google. I operate a fairly large network, which includes a very large backbone and a number of very large data centers. I actually don't think that OpenFlow itself is particularly interesting as a protocol. I think that it is the leading instantiation of software-defined networking, today. And I'm certainly a big booster of it. We've been involved in it for a number of years, and you can do a lot of very useful things with it. And I'll talk about some of those in the abstract in a little bit. But fundamentally, I actually think that we're over-focusing on OpenFlow, honestly. And what we end up hearing from a lot of the vendors is that we're going to end up with this all-seeing, all-knowing set of applications with total global visibility of state, et cetera, et cetera. That's a good thing. I'm not against that. Some people are against making forwarding decisions that are not congruent with the actual forwarding path. I'm not one of those people, and we can talk about that later if you're interested. But what we end up with today for OpenFlow is really something more like this. Which is, you know, it's a good costume, but it's not what you're being told necessarily. So SDN in general is very interesting to us at Google. And this is primarily because we run in environments that are sufficiently scaled out that cost savings of between 5 and 20% from a provisioning perspective are quite large in terms of total monetary return, basically. And so we have to be very careful about how we provision state, what state goes in the network, how we use forwarding state in the network. And we also have to be careful about how we use network resources. In general, you know, not to diss on any of our wonderful vendors here today, but in general, you're being overcharged for what's on your RE or et cetera, right? You just are. The technology is 5 years old. The CPUs are kind of underpowered. The amount of memory you're getting, it's all right, I guess, for your desktop 5 years ago. But by and large, you know, you're being overcharged for this stuff. So this is kind of why SDN in general is interesting. So I'm not going to focus on OpenFlow for my actual presentation. There's plenty of material in the backup slides, and I think these are going to be published on the website if you're interested in the discussion of how we can actually take multidimensional flows, map them to hardware, et cetera, et cetera. And Kurt talked in the abstract a little bit about some of that with regard to the 2.0 work. I'm going to focus on SDN. So basically, SDN, and I don't know actually how many people are familiar with it because I've been living in this very rarefied environment for the last 2 years where it's something I've been working on very closely. The main thing with all of the protocols that implement SDN is that you're removing distributed decision logic and database distribution mechanisms from the network elements. That's basically it. All of the slides that Kurt presented and that Guido presented are basically to that. You're moving state into the controllers and the applications, and you're pushing state down to the network, and you're only pushing the state down that you need. That's basically it. And all of them have the same thing. Now, a lot of the time people will make the argument that SDN is actually going to minimize the complexity, and that's true, but that's only true on the switches. So when we talk about this, we have to be very careful. There's certainly a lot to be said for moving complexity off of these devices that are difficult to manage and involve a significant amount of irregular policy decomposition in order to do so. And so moving that complexity elsewhere can have benefits, but you have to be careful when you're doing it. So the concept of SDN has been around for a long time, actually. So Guido pointed out that the first version of OpenFlow was around in 2007, basically, inside of their group, published in 2008. But well before that, there have been a lot of protocols that have attempted to do this, and they certainly make for interesting reading if you're actually following the space. I've included a bunch of them here. OpenFlow 1.0 looks a lot like FlowSpec, quite frankly. FlowSpec was never widely implemented or used, but Pedro did a good job, and it's kind of prescient in a lot of ways. It also looks a lot like GSMP. Again, not something that most people here are probably familiar with, but certainly an interesting protocol. These days, SDN is instantiated really in 3 places, arguably, but really 2, PCE and OpenFlow itself. The difference here is that OpenFlow is pushing forwarding state directly to a hardware abstraction layer, and is basically eliminating all portions of the decision process and all bare protocols in terms of routing protocols. PCE obviously is based on you having RSVPTE deployed, ISIS, et cetera, and so from the network element software complexity side, obviously that's a bit higher, but it is readily implementable today because only your LERs are going to be running it, et cetera, et cetera. So I have a timeline which it turns out is redundant because Guido had more or less the same thing. I wanted to point out that the dumpy engineer is 1.1 for me, and I wrote part of the spec, so I have to take full responsibility for that costume. There are a lot of very useful features in 1.1, such as MPLS, tags, imposition, push pop, yada, 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 pretty basic stuff. But honestly, the protocol is still in its infancy. And even in 1.2, for anyone who's familiar with a well-designed routing protocol, you're going to notice a lot of inefficiencies and issues. So it's definitely a work in progress. And we're interested in promoting it, and we're interested in getting it to a point where we can actually do the things we want with it, because we can't do all of it just yet. If you want to talk about specific applications, come see me later. A lot of it is based around the 2.0 stuff, which is quite complicated, and I'm not going to put everyone to sleep with that, because I'm sure that we're all tired as it is. So why do we actually care about SDN? Well, I covered some of this in the introduction, but basically it's cost, because most of what I do is cost optimization with bounds for performance. So from a cost perspective, there's CapEx, obviously, and I covered a little bit about why I think that we're paying too much for compute resources on routers, ultimately. But that's not going to go away for a while, as Kurt pointed out. It's not like all of your distributed protocols are going to disappear and your vendors are going to sell you these awesome blades that run nothing but OpenFlow. It's just not going to happen for a little while. So what we do want to do is move the heaviest workloads off of these devices and make use of total network state as best we can. So a lot of the times it's just not efficient to carry really granular information about network state to all of the devices for obvious reasons. Centralization allows us to do some interesting things with that state and apply some pretty well-known optimization techniques to do things like cross-stratum optimization or better traffic engineering. From a CapEx perspective, this means that I'm buying less physical plant, basically. So unlike a lot of people here, I'm actually very into OpenFlow in the WAN. Because I run a very large backbone network and there are a lot of inefficiencies with regard to the way that traffic engineering works today. Typically people will over-provision their networks to avoid the complexity, and there's a whole argument there, obviously, about whether we even need MPLS, et cetera, et cetera. But ultimately, I'm trying to run my network relatively hot to within my performance bounds, and I want to spend as little as possible. A lot of the time, that's just not possible with today's northbound APIs, and SDN, OpenFlow, and PCE both give me the opportunity to have a reasonable, standardized northbound API to these devices to control forwarding state for better traffic engineering. It also allows us to reduce interdependencies between protocols. A lot of the time, you'll find yourself bending over backward to do something stupid with a routing protocol, just because you need the state in there. And obviously, you want to minimize that, but it would be better if we didn't have to bend over backwards at all. And so being able to do direct state imposition based on a regular rule set from some centralized location is obviously pretty helpful there. The reduction of the complexity of distributed control systems on network elements is obviously a good thing too. I don't know how long everyone else takes to test their code and get it approved for production deployment at this point, but for me it's a little while. And so the less features I have to deal with there and the less complexity there is, the faster I can roll new code and the better it will be. And then, of course, you can implement innovative new technologies on top of it. So this is basically the optimization techniques that I was talking about. You're able to design your own protocols. If you're into such things, obviously there's a world of pain there for you to explore. From an innovation velocity perspective, which is primarily speaking to the last point, being able to partition resources means that I can use pretty well-known development techniques in order to start to do basic software engineering for new protocols very quickly. Right now, it takes me a long time to get a new protocol into a device. I want to move faster. And that's my presentation. Thank you.
Well, that was like drinking from a fire hose. Anybody have any questions? Jake.
Hi, Jake Kuhn, IP Infusion. So this is actually directed to Ed, and I was wondering what your opinions were in terms of, since you're now with the SDN model pushing state around the network from the control plane to your forwarding elements, how that impacts things like dynamicism and the ability to recover from network failures. Are you seeing that as a potential obstacle that needs to be overcome? Is it going to introduce problems? And also, how will this change in terms of pushing the hardware manufacturers, silicon manufacturers, to for implementation of any kind of buffering of state tables or things to take into account the fact that you're now transferring state across the network from a control plane?
Is this for me or was it for the group? I'm sorry.
Was it generic for everyone, or?
Well, more towards Ed, but I guess anybody can answer.
Okay, so I guess obviously if you're trying to do some sort of fast local repair, it should be local. And you should be able to push the state for the local repair, i.e. the offline decisions that get made for what happens in the case of a failure down to the devices, but you still have to have a fast local control loop in order to affect this sort of thing. So honestly, it's a pretty trivial problem as far as I'm concerned. It's not a particularly big deal. As far as the hardware vendors, I actually think it's too early to say what's going to happen there. I mean, it's not clear how well developed the OpenFlow ecology, such as it is at this point. It's definitely an emerging market and people are interested, but I'm going to hold back and wait to see what adoption rates are like.
Anybody else want to take a whack at that? Let's go here and then here.
My name's LJ Wabker. I work for Cisco. I do hardware and data plane design for the 9KBU. One question primarily for Ed and one sort of for the panel. For Ed, what I think I caught from the presentation was if your two big pain points are CapEx and the ability to do more granular traffic engineering within the data plane, and by traffic engineering I don't mean MPLS, I mean picking and choosing traffic and getting it somewhere. In the hardware world, those things are borderline mutually exclusive. So if you have to weight them against each other, where does that weighting come down?
Let me reiterate your question to make sure I understand it. You're saying that carrying additional state is costly.
Yeah, the functionality to do more and more granular traffic engineering in the data plane is expensive.
I disagree. And
Okay.
The reason that I disagree is because it's based more on the network architecture than on the hardware. If you can impose additional encapsulation types that aren't necessarily even well-known protocols in order to affect this sort of traffic engineering, then I can reduce the total amount of state by doing effective aggregation, things like this, right? So.
Okay, so there's a significant component of discipline in the network architecture.
Yes. There has to be. I mean,
exists.
of course. You know,
Okay.
I'm trying to protect my hardware as much as possible.
Not everyone makes that assumption.
Yeah. Also, if you're not involved in the OpenFlow 2.0 efforts, you should be. Just saying.
Okay. And then for the panel, and that may be 2.0, to what extent is the spec planning on discussing how to make those trade-offs, or at the very least how to get those trade-offs visible in the community? Because they do exist, and at some point we have to choose A over B. And we're going to need help from the industry to figure out which is more important.
Kurt is in charge of the 2.0 working group, and I'm going to defer to him.
I'm going to ask to hear that question again. I was mapping it to a different thing, and so the 2.0 support, yeah. Say it again.
To what extent does or will the spec illustrate the fact that these trade-offs exist, and that as vendors we have to decide what things we want to build, and as consumers the other folks have to decide which things they want to optimize around? Because at some point you won't be able to do both.
Yeah, so obviously a very complex question here. And I mean, it's kind of beyond the spec to talk about those trade-offs exactly, so much as to provide enough structure for people to move forward and enough freedom for people to do a lot of different things. And I think we're moving in the right directions on that from a 2.0 perspective. I mean, I was hearing some discussion about you were saying about the contradictions, and I have a hardware background, and I understand that's true, but if you look at I mean, maybe that affects gross margins, but if you look at the cost structures for, say, network hardware vendors, there's a lot of costs that go in besides just the raw product costs, right? It's not just the COGS that determine what you sell something for. And conceptually, if you play that forward, if we are able to reduce the number of software engineers we need and reduce the amount of QA that we have to do and yada, 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 now you can talk about, and it's not necessarily us, right? There can be some upstart that comes along and produces something using a different business model and so on. So it doesn't necessarily have to change the raw, chip size, et cetera, in order to lower the cost of the overall product, because it could be somebody's operating in a much different business model and has different gross margins, right? This stuff can be enabled by 2.0, and we don't have to I don't know, what would that be, section 4.6, trade-offs? No, I don't think we're going to have that.
Okay, thanks.
Yeah, just quickly to add to that, I mean, I think the OpenFlow specification, if you look at it, its philosophy has always been just to define an API, for the switch. It makes zero recommendations on how to build the switch. And in fact, it doesn't even sort of contain a functional model of how a switch should behave at all, which to a certain extent is a problem, but I think we're light years away from giving you good guidance on what to do there.
Yeah, I guess the message there is that you can totally blow up your devices if you mess it up. It's, it's a loaded shotgun that you just pointed in your face. Obviously, you should be careful. And you should, talk to good vendors like Guido that are writing applications for you, hopefully, or at least informing your choices there. So.
Go ahead.
Jay Hennigan with Impulse Advanced Communications. I certainly see some powerful benefits to OpenFlow as opposed to the conventional way of configuring individual devices on a network. What I'm concerned with is how gracefully does it break? If I have a switch that fails now, I have traditional things such as HSRP, VRRP spanning tree that will route around it. If my network can't get back to the mothership because the mothership is broken, and the only way it knows how to get back to the mothership is from the mothership, I suddenly have a complete meltdown that seems like it's going to be very difficult to get out of.
I'm happy to take this one. We confirmed that experimentally. You can have very effective meltdowns that way. So the general question...
You can smoke
there's
yourself
several
at any
questions
moment.
that you need to solve. And one is the question of in-band control. Basically, if you forward your control traffic over your data plane, and then you get, since you have a number of issues. Some are related to stability, some are related to feedback loops. There's a related some people that run SDN actually using dedicated control networks or physically separate control networks. I think at this point we understand the problem space, we understand the trade-off of solving it, but it's a very real set of issues.
Yeah, I mean, you really have a bootstrapping problem, right? And you have to bootstrap some level of topological awareness and awareness of controllers, et cetera, whether it's by static configuration for whatever the topology is, because theoretically you have access to what that graph is and what the attributes are, or whether you're going to design your own protocol for discovery at this point. So all that OpenFlow does, to reiterate, is allow you to put state in the network. That's it.
We also touched before about how we may want to have more intelligence in the switch than it seems at first when we talk about, well, we're just going to abstract this all out to some external controller. And I think what happens under failure conditions is the kind of thing that, well, we probably want to sort some of that out in the switch. And none of that's in the standard yet, right? And how much of it will go into the standard, I don't know. So we're going to continue to be in this place where I think, Guido's firm and other firms and their partners like the hardware vendors will find ways to solve these problems. I mean, we're not unaware that these problems exist, but they won't be standardized. So you'll be in that partner kind of a situation, depending on which problem you're doing. I mean, if you're running an open vSwitch, well, then you don't need a hardware vendor to produce that for you. But we need some maturity. It's a bunch of interesting problems with a bunch of motivated, smart people working on it. But yeah, be patient a little bit.
Igor.
Hey, Igor Goshinsky, Yahoo. Ed, you were talking about doing short control loops on local devices to do fast local repair stuff. What routing protocols are fairly good at is dealing with a multitude of outages happening at once. So when you do a fast local repair that you pre-calculate ahead of time, you need to figure out how many things you're going to account for locally, and after you fail to account for all of it, then you go upstream. As opposed to a routing protocol running a switch that could say, all right, I just lost 16 links. All possible local repair options that you pre-programmed to me are gone, but I do have other really hokey ways around it, because as long as my Dijkstra graph is still intact, or at least if there's any feasible paths, I'll get to it. Where do you think you draw the line for number of faults that you pre-program local repair versus which you program, willing to go talk to the mothership, or, at what point do you start saying, you know what, I want to put a lot more state in the local device than in the RIB of the local device for a longer-term control loop than a FIB switchover, but shorter-term control loop than going to the controller?
Yeah, so obviously it's kind of a sliding scale there. The further my controllers are away from the devices and the longer the decision algorithm takes to run, the more local state I'm going to have to program in order to account for these sorts of failures. But honestly, if a 16 links failed on a device, I probably want it to go away completely.
Yeah, but it's not necessarily 16 links fail on one device. It could be that
I thought you were
saying
saying on one device there, but yeah. No, I mean obviously, like if hypothetically I have a bad architecture, right, and I have one controller for all of the United States, right, and I have several problems in one region, and I have to deal with cross-country latencies in order to get failure information signals back to the device, run the whatever it is that's running, and then get information back. That's obviously suboptimal, and I'm going to have to take that into account and program additional state. So,
I mean, it's pretty clear that, a control loop that has duration shorter than the RTT between the controller and packet processing time in the switch is going to be hard to implement, right? It's kind of an upper bound. Tony.
Thank you. Anton Capella, 5 9s. First response, I like the concept that there's a HAL in the workings here to be improved for decoupling these two features of modern devices that we buy. It seems like someone's going to have an opportunity here to write some pretty innovative stuff with the control plane, and I can't wait to see what we get. The other hand, I'm curious what you might all think about the latter part, what we could expect, and that is along the lines of active networking. So for example, we're talking about just programming stuff into control planes today. Of course, GE research hasn't been touched for like 10 years, but the concept is still in my mind that at some point, this kind of division of computation and transportation of information itself becomes blurry. And maybe we ought to ask ourselves here, is there any interest in that? Did the future, if you will, working group participants yet to this date think about applications being closer to these types of frameworks versus farther from them?
what do you mean by applications?
Something to mangle some sort of packet content.
Yeah, you mean a network application?
Sure. I mean, it's one category of ABN, right?
Yeah, so I don't know if you've seen the debates that are going on in the SDNP proto list in IETF right now, but we should talk afterwards. Yeah.
Sure. Anybody else? Oh, I meant this for the whole panel, if you could. It's okay.
I think it will get closer. I mean, essentially by creating this freedom, somebody's going to create a pathway to make those closer than they currently are. And is the market going to adopt it? Is there going to be enough value add in that? I guess we'll have to see.
Well, in your model, I guess to refine the question, does this look like a service, quote-unquote, concept in the switch? Arbitrary interface happens to route to some CPUs, or is there a more direct path inside this concept to, say, redirect some traffic within the chassis to, say, an integrated layer 7 aware device or so forth? Like how do local services look to this model, if that's even something you consider to be special or separate?
So that's I don't know if this is the right way to answer this question, but let me just try. There's some work going on that's trying to do some kind of melding between what these off-box control planes, the controllers, do, and what on-box distributed control plane would do. So there are services that we know about today that might be able to coexist with these other services, and they might not look different, or they might have APIs exposed. So the PCIe was an example that Ed gave. There's Alto, and there's any other arbitrary one that people want to do, right? So in some ways, there's this hybrid mode that's emerging that kind of is trying to address that.
I'll be mindful. Thank you.
Others? That it? Anyone else? Okay, thank you very much.
Thank you very much, folks, for that excellent discussion on OpenFlow. We have a survey giveaway from yesterday's survey. Again, a reminder that we're going to be giving away a prize tomorrow and Wednesday as well. The only thing you need to do to get these wonderful prizes, well, two things. You need to fill out the survey, and you need to actually be here during the second session of the day, right after the break, the morning break, when we actually announce the survey winners. So, and I just want to remind you, with a sample set this small, there is a really good chance of getting something to go home with. Just fill out that survey, please. So for yesterday's survey, I'd like to hand this out to Jeff Houston. Congratulations. You know, Jeff actually impressed us with a really visually stunning talk a couple of nanogs ago. What was it? I remember you like took pictures and you marked it up, so maybe you'll be able to see it again. That was a Wacom tablet. Anyway, SoftLayer has donated the giveaways for the surveys this nanog. We have a little bit of time before our lunch break, so I'd actually like to get Martin Levy up here for a lightning talk. Where is Martin? Hey, here he comes. Yeah. We had a submission that we're able to actually shoehorn in here.